Okay, so now briefly about conductors. So what are conductors? Conductors are the friendliest friends you can have in electrostatic problems because they have very basic friendly properties. So what properties can you state about those? Well, first of all, the electrical field is zero inside. Because if there was a residual field inside, any charge that is mobile would exploit this to fly away and suffer a force and therefore move, and therefore change the charge distribution, therefore eventually annihilating the field. Okay, so that's the first thing. The charge also is equal to zero inside because the same reasoning, if there was a charge in there, it would like to fly out. Kind of same statement as this. So so any charge that your conductor has flies to the surface. Okay, once again, a conductor, if you've got a finite charge in there, charges will repel, and that means they go as far away as possible from each other, and therefore they jam up at the boundary. Okay. Now, very importantly, a conductor is an equipotential, and that's the one we really want. Okay, so what's an equipotential? It means that the potential is the same throughout. There's a big lump of matter, it's a conductor, and everywhere in this conductor and also on its surface, the potential is fixed at a certain value. Okay, so so that's it. And then final thing you can write also is that E at the surface it's perpendicular to the surface. Okay, once again, in a sense, these are slightly tautological reasonings here because it's also a kind of consequence of all these facts, mostly that E is equal to zero. If there was an electrical field that was tilted at the surface of a conductor, it would mean that the charges at the surface of the conductor would feel a force to move them along the surface. But they don't, because if there is, they move. They move as long as they haven't canceled the field. And at some point when they stop moving, it's because the field doesn't have a component anymore inside the surface. Okay, so that's what it is. So what's the statement here really? It's again an ingredient that you would use in Gauss's law. You would now do a pillbox on the surface of a conductor, but now the field inside the conductor is zero. Therefore, in order to saturate Gauss's law, you put all the field just outside. And the field just outside a conductor is equal to sigma over epsilon 0, whatever the sigma is at that point. Okay, so that's the kind of thing. But you see, that's why these conductors are friendly, because you see immediately that they are cases of Dirichlet boundary conditions for the solution to Poisson's equation or to Laplace's equation. Okay, so if I have a conductor somewhere, I have a conductor here, I tell you that there's a certain potential here, which is given by some number phi 0, and then I ask you to compute the potential in lots of different places, then you can say, okay, my conductor, I don't care what happens inside, I want to know the solution to Poisson's equation in the space around it. The conductor itself forms the boundary of my space. And I know the potential on this boundary, therefore that's Dirichlet, therefore I fulfill, my friend Green is really happy. Okay? And therefore the solution for the Laplace equation in this case, empty here, is going to be unique. Okay, so conductors are really the simplest boundary conditions you can find in electrostatics. Okay, how much of the physics of conductors have you done in your first course? maybe one little test on you. Let's say that I have a perfect sphere here, and let's say that inside this sphere, so it's a metal sphere, but inside I've got some lump that's been machined out, okay? And in that little lump of space, I have a charge Q here. So this external shape is a perfect sphere. The bulk is a perfect conductor. Inside this perfect conductor, there's an empty region, which is a complete mess. So somebody at the foundry, they just, the thing degassed at the wrong place. There's a bubble in there, and there's a charge that's in there. Okay, so how can I think of this? What does it look like from outside? Yeah, and does everybody get that? Perfect conductor, okay? Therefore, there's a positive charge Q here. Therefore, there has to be canceling charge on this internal surface here to completely screen that Q. But that means that if I need negative charge here, I need to have positive charge distributed on the outside. However, the distribution on the outside is absolutely perfectly uniform, irrespective of the shape of the inside cavity. Depends only on the total charge inside the cavity. Okay? Therefore, from the outside, you cannot do anything electrostatic in order to determine the shape of the internal cavity. You need to do dynamics if you want to do that. Okay? And how should you think about this thing here? You should think of this as 3 different boundary value problems. So first boundary value problem could be one where you've got the space outside, and then the boundary is the surface, the external surface of this conductor here. That's one boundary value problem. The second one is quite easy here because it's a conductor, but inside the conductor here, but outside the cavity, I also have a boundary value problem. Now I've got 2 boundaries, the outer one and the inner one. And on the inside, I've got yet another boundary value problem, okay? Because I've got this boundary here, and then I've got this this thing here. So okay, you can think of all these things as these different cases. Okay, so is that just simple things. Now in the notes, there are some details about the surface charge on a conductor with the field. So for example, maybe just expand this on this. So E at the surface of a conductor is just sigma over epsilon 0 times n, where this is the charge density. So the surface charge density at a local place, it can vary. And this thing is, of course, the normal, the local normal vector. So for example, if I take a little patch here, right, the normal vector is going to be coming out, something like this, and there's going to be a certain surface charge density here. In this case here, if the radius is just big R, the surface charge density is just going to be little q divided by 4 pi r squared, because the charge is uniformly spread on here. Therefore, the field at any point here is directed outwards in the radial direction if I adopt spherical coordinates centered on the sphere. And the intensity of the field is just going to be this thing, q over 4 pi epsilon squared divided by epsilon 0. Okay, so we would expect. So that's a case. So there are lots of questions you can ask about conductors. You could ask, for example, if you have 2 conductors next to each other, what's the capacitance and all these things. This is in the notes. I'll let you have a look at it because I presume you've done some business with conductors in your first course. like, have you seen the notion of capacitance for conductors, right? So it's the kind of capacitance is the relationship between the charge of a conductor and the voltage at which it lives. Something that has a higher capacitance has a higher charge for the same voltage. Okay. So, so that's the thing. But I'll let you revise these things in the notes because, again, I think these are acquired